to talk today and tell you all some of the work that we're doing here at the University of Utah. My talk today is entitled How Machine Learning is Changing the Way That We Predict New Crystal Structures. So I'll just dive right into it. First off, I'm from the University of Utah. It's located in beautiful Salt Lake City. You can see it right here. My lab is right here in the bottom right-hand corner, and you can be up skiing in the top right-hand corner. So I see that this is a meeting of the Materials Advantage chapter at Suez University. Here is a group of our Materials Advantage chapter. Earlier this year, we went and did a group touring trip this winter. Okay, and then as I talk about the research that's been done today, just realized that I didn't do any of it. This was all of the great work of my students, and here's a current snapshot of the group, and I'll try and call out individual contributions as I get to them. Okay, so about, what was it, maybe almost 6 months ago, there was at the Fall MRS meeting, these two papers came out in the middle of the Fall MRS meeting, which talked about, one came from Google's DeepMind paper, which basically said that they have discovered a huge number of new materials, 2.2 million structures, they say they found. At the same time, another lab had come out with this tool that could robotically start to explore materials at a really high throughput. So machine learning and crystal structure prediction is certainly in the news of late. But what I'd like to do is step back a little bit and talk about some of the progress that got us to that point, right? And I'm going to do it by comparing it to the field of image generation broadly. So this comes from a tweet from a guy named Ian Goodfellow. Ian Goodfellow was a graduate student at the University of Montreal, and he's the guy who invented the generative adversarial network, which is a machine learning, computer science architecture for creating something new. In comes random noise, out comes something. And in this case, that something is pictures of people. And you can see on the far left, this 2014 image, that the very first ones that it turned out were not the most convincing. Like, yeah, it looks like a face, but it's not going to fool anybody. But look at the rate of progress over time within a really short period of time. And we could add more if we wanted to in 2024, how good it's gotten. It's gotten downright, very, very, very convincing. So let's ask ourselves the question, can machine learning actually generate something new? Because it kind of looks like it can in those images, right? I remember the thing that really convinced me was in 2022, I think it was, right? Or maybe it was 2021, when DALL-E 2 came out, and people could all of a sudden provide this text prompt and out would come these images that match it. And yeah, for the skeptics that said like machine learning is only interpolating between points, it can never really extrapolate. Boy, this looks generative to me. Like this is actually generating something that no humans made before in a useful way. Similarly, another real turning point for me in realizing the value of this was when people talked about how good things like GitHub Copilot or ChatGPT are at generating code. So I tested that out. I made this YouTube video that you can find on YouTube where I actually talked to my computer and it would take my voice, turn that into text. That's a generative model. And then it would take my instructions, what I was asking it to create. I was trying to make it create this figure of grain size versus strength, the Hall-Petch relationship. And it was able to generate all the code. And in a discussion sort of dialogue way, I could say, oh, I don't like those colors, or like now I want tick marks and minor tick marks, or, make me a dual, plot with one stacked over the other. And it could generate these figures in real time, which is so impressive, right? And then obviously the two big papers that came out in November, and then Microsoft, a week afterwards, talking about now conditional generation of new materials. So it's an exciting time, and we're really just at the cusp of it. We've seen even cooler things. This was only, 2 months ago, less than 2 months ago. We've seen OpenAI come out now with text to video, where in this one, you'll see that this video that you're seeing here was the result of a prompt. Within like 12 hours after this came out, people had already come up with generative models that added sound appropriately to this video. So it's sound, you can actually hear her footsteps, you can hear the cars honking, the hustle and bustle of the street. It's all been added. So I don't know. When I think about what can't it do, it's like, I don't know. Generative models are pretty amazing right now. And one of the reasons why they're so great, especially for material science, is that we don't have to do all of the heavy work up front in developing these algorithms. We sort of benefit from being in this field adjacent to the computer science, where we can use the tools that they are building. So for example, here you see 4 different machine learning models for generative AI, and they've got kind of their strengths and weaknesses, and I'll talk about some of those later, but the fact that we can just use them makes it really easy for us. That said, if you try and use generative models for material science tasks, you might be disappointed at first. Like here's me going back to Dolly and saying, give me an oxide crystal structure with offset layers of corner shared AlO6 octahedra and rare earth filled interstitials. And you guys on this call, you might be more aware of what I'm looking for, which is a crystal structure. And instead, this is the best it can come up with, right? So how do we fix that problem? To fix that problem, I had a couple students work on this. It was led by the guy on the left, Michael Alverson. He now works for Google, but it had support from Sterling and Ryan as well. And his idea was, well, what if we generated the information in the sieve card itself? What's the sieve card? The sieve card stands for crystallographic information file. Maybe you've opened one of these before. If you have ever used Vesta or some sort of crystal imaging, crystal maker software, for example, then you have to give it a sieve card, and it has all the information to create a periodic repeating crystalline lattice. And that's an important thing because this field of generating something new for materials and chemistry has been stuck for a while with only being able to make molecules. We could make molecules, but we didn't know how to make this molecule stack in 3D space. And sometimes the stacking is really what gives it the right properties. For example, that's where your dipoles and whether they cancel or not comes into play. So the way that these actually crystallize together was an unsolved question because we had no invertible representation. We had no way to represent that molecule that we could invert, meaning we could pass it through a generative model. So I'd love to say we were the first, but in fact, we were sort of tied by our friends at MIT, Tonio's group, who came up with a very similar approach as we did at the same time, basically. And if you look at both of these approaches, they're similar, but the key things is that we're going to encode the crystallographic information file information. So for example, here's their A, B, C values, their alpha, beta, gamma. You see where the atoms and the bases go into here. So that's this FTC approach that they came up with, and we came up with crystal to ping, okay? And just to jump to the lead, like these things can now turn out some really convincing and very interesting structures. So how does it work? Well, in the early days, we were using a GAN architecture. That's the same thing that the guy tweeted about earlier. GAN stands for Generative Adversarial Network. And in this kind of confusing architecture, I'll describe what's what. You have a generator. This is the thing that takes in random noise, right? And spits out a new sieve card, basically, a new sieve card that you hope looks like a real material. Meanwhile, the discriminator up here, it takes a bunch of known materials and your fake materials, and it's going to try and figure out which is which. And when it gets it wrong, we penalize it, and we try and update the weights of the discriminator and the generator in response to the rate at which it's correctly classifying or incorrectly classifying the data. So you're really pitting these two things against each other. You're trying to make the generator fool the discriminator and the discriminator catch the generator. And we've done a few other things, tricks along the way to make it work better, but that's the main idea of it. So let's look at the sieve information. The sieve card, when you open it up, it's just a text file, and there's actually not that much info here that you need, right? ABC, alpha, beta, gamma. The space group number gives you all the symmetry from that one number, and then the basis, which tells you which atoms are there that you apply the symmetry to. So from that basic information, pass it through Vesta, and you get a 3D structure of material. And there's tools like PyMatGen that make it really easy to extract that data. There's also really good databases out there where we can grab lots of examples of real crystal structures to train our models from. So here's one where it has 300,000 structures, and about half of those have all the information that we need to train our models. So that's still quite a bit of data to learn from. So now comes the time where we need to introduce a representation. So we could have done this with a single, right here you see a matrix. We could have done a single vector, like one row of this matrix, right? We can put the ABC, the alpha, beta, gamma, the space group, and then you could put the atoms and the basis technically. But it was a little bit easier if we did a matrix, because then for each atom in the basis, we could put the type of atom, and then in the subsequent rows, we could put its position. Right. It also made it more stable if we averaged the A, B, C values and the alpha, beta, gamma values. We averaged those rather than taking a single shot at it, because generative adversarial networks tend to be poor trainers. They tend to diverge as they're working towards a solution. They end up not being stable, and they diverge. So we did a lot of work, and we finally got it to not diverge, but rather to converge to some solution. And we're excited. We're ready to open up the sieve card. We think it's going to be a winner. But then we get some errors, and the errors are saying something about the fact that we're picking a space group that's incompatible with the lattice parameters, and we're like, oh, I see. We were basically giving it ABC values that weren't equal, And yet we were saying that it was a cubic structure, so that doesn't work. So we had to go back and we had to introduce some post-generation constraints on our materials that came out of our model. Basically, we had to say if the space group is in this range, then we have to make the lattice parameters look like materials in that range. So we average them together. We set the angles equal to 90. We had to do the same thing with all the other crystal systems. Okay, we got that fixed. Then we go to open it again and we get another error. This time, it had to do with the fact that if we were assigning an atomic number of, say, 22.145, the Vesta didn't know which atom to use. So I naively at first was like, oh, okay, just round it to the nearest atom. But the problem is that if you do that, you might end up with a compound that has, 52 different atoms, because we're allowing it to have 52 different atoms in the basis. And yet in nature, we know that compounds don't typically exist with 52 different atoms in them, right? In fact, Pauling pointed this out 100 years ago with his famous sort of fifth rule of parsimony, which basically means that things tend to be simple structures. They tend to be binaries, ternaries, maybe quaternaries. By the time you get to quaternaries, that captures, the vast majority of compounds that we find in nature. So 52 different atoms, that's not very likely. With the way that we fix that is via clustering, where we can take these bunch of different atoms and we can force it down into like a k-means 1 or 2 or 3 version of that, where you force it into a binary or ternary. So we finally did all of this and we got our GAN to converge, and we could take a look at what it spit out, right? And I was excited to see what sort of crystal structures it created. And this was on the bottom left, the first one, and it was awful. It was so bad. I remember telling my student, like, okay, it was a really good idea you had. I love that you built it and you got it working, but this is not good enough to ever use or to show anybody. This is not a real material. And he's like, okay, yeah, but let me try a bunch of other versions. And he started trying many versions of GANs to follow, where he would add different normalization or convolutions or LSTMs, and they kind of started to look better, but still really bad. So if I compare it to sort of our image progression, I would say that these early structures looked more like the 2014 face than the 2021 face. They're not fooling anybody. They're not very good. They're not realistic. So what do we do with them, right? Well, one thing, if we're going to try and make it better, is that we should probably go beyond our traditional GAN architecture, because it has some limitations. And the biggest one is this idea of a diminishing gradient or a vanishing gradient. What do I mean? At the very end of your neural network, the discriminator typically comes down to a single node, and at that one node, you pass it through an activation function. In this case, it's the sigmoid equation shown right here. And the value of that node A comes by plugging into the incoming values of that node X through this equation. So what that really does is if your value of X is really negative, it flattens that A value to 0, which might represent that it was a fake material. Whereas if it's a big positive number, it flattens it to 1. And there's only a small region in between where there's ambiguity, which people like. Computer scientists love the sigmoid function because it's so non-ambiguous. But the problem is that, okay, let's say you start making a more and more realistic material, or if it's a really bad one, the slope here is really low from this equation. And the slope is what we use in updating our models via backpropagation. So the better you get, the less and less useful information you're giving back to your model to make tweaks, which is why it was sort of getting stuck with these not great materials. So the good news is that there's many other different things that we can do here that don't have vanishing gradient. The best one that we ended up with was a Wasserstein GAN. A Wasserstein GAN is a version of a GAN, but instead of a sigmoid at the end, instead of compressing it down to a single value, you compare the entire distribution by reframing it as a cumulative distribution function, and you're looking at the area under the curve between two different materials. So in other words, you had this big representation of a material, this giant big matrix, right? Instead of trying to flatten that down to a single value to make the comparison, take the entire amount of information, make a distribution function out of it, and compare those whole distributions. Now that did a lot better. So now the year is 2021, I think, and I went to the fall MRS meeting and I showed them this, a group of chemists, and I said, can you pick the 4 that are real here from the 4 that are fake? And if I told you like the bond lengths or even the atoms involved, the chemistry formulas, right, or a number of different other things, it would make it really easy. But at least it's a move in the right direction to start fooling our fellow chemists into really maybe thinking that we can generate something new here. But it was still not very good. And the biggest problem we were running into was this, right? We would generate the basis from the sieve card. And then from that single number of the symmetry, we would go from these atoms to all of these atoms. And that's when it went off the rails. That's where atoms started getting put on top of each other, and bond distances in that weren't being respected. So we corrected that by having a new representation. The only way we're going to get around it is by actually giving the atoms and the bases a chance to learn what an appropriate distance should be. So for example, each one of the columns here in this matrix along the top represents a unique atom in our basis. And each one of these rows also represents a unique atom in the basis. And in this period in the middle, this section in the middle, that's where we allow the direction graph to be created, where we learn what the distances should be. In fact, one of my students, Sterling, pointed out, hey, if we do that, we can actually map those distances in the X, Y, and Z directions instead of just the Euclidean distance. And if we do that, then this is just a colored image, which is really cool. This colored image on the bottom right, that represents a material. That is a crystalline structure, right? It's kind of weird to think of it, but that is a crystalline material. It's all the information in the sieve card that's now been encoded in this way. So that's why he called this crystal to ping PNG, because now that you treat this as an image, that makes it great to use all the different machine learning models out there, things like Imagen or Dolly or Palette or whatever the other ones are out there, Midjourney stuff. You can use that with this representation to generate new materials. So let's walk through how it works. Direction graphs can be constructed in these three directions. So let's consider the X direction. If I've got these four atoms going from atom 1 to atom 2 in the X direction, we'll call that a distance of S. But going from 1 to 3 doesn't change in the X direction, so it's 0, right? So you could finish populating this direction graph for all your atoms in the X direction. Then you could do it for the Y direction and the Z direction, right, and so forth. But the catch is that our generative model is going to generate one of these direction graphs, and we then need to back calculate what the appropriate positions are, which is not so bad for the first one, right? You say, okay, from atom 1's perspective, I know where atom 2 and atom 3 and atom 4 is, but the catch is that you have to do that for every atom's position. So for every atom's perspective, for example, if iteration 1 looked like this on the left, now imagine from atom 2's perspective, it guesses where atoms 1, 3, and 4 are, and they don't exactly match up. Same thing for atom 3 and for atom 4. These things don't exactly match up. So I remember telling my grad student, like, well, all right, just take the average though, like put it on the average position, which we did. But he cleverly said, okay, I'll do that, but I'm going to hang on to the variance that existed in these different dimensions. Like, how uncertain were we? Was it really pretty close, or was there lots of ambiguity? And we're going to use that for a measure of goodness of the generative model. So here you see, we were able to average it down to a single point. And then using this approach, we were able to generate some really convincing structures. So just how good are they? Well, let's compare them. I'm going to compare the GAN model, the very first one, the bad one, with the Wasserstein GAN, which was significantly better. And then the best one that we've gotten working so far is based off of diffusion models. And what you see is in these different columns is you're looking at the uncertainty in different aspects. Like when it predicted a space group, what was the uncertainty squared? 2497, that means it had no idea which space group to use. But by the time you got to diffusion, the uncertainty squared was only 6, meaning it pretty much knew which space group to use within a 1 or 2 or 3, right? Pretty darn close. And what I'm seeing when I look at this data is basically about an order of magnitude improvement as you go from GANs to Wasserstein GANs to diffusion. And that pretty much tracks with the output of these models. For example, when I look here at our what's called the so-called vanilla GAN, like the basic GAN, I see that the unit cells are way too big. The types of atoms are silly, like they're only giving out, it's what we call mode collapse. They're only creating transition metal and actinides. It's not using the whole span of the periodic table. Just not very good. The Wasserstein GAN was significantly better. You're seeing more variety and variability, both in the types of structures, the shapes they create, the types of atoms that it's using, but these are still not very good. And yet, by the time that we get to diffusion models, now I can say that we're getting diverse and symmetrical crystal structures that are looking pretty convincing. Another way to compare it would be to compare the distribution of data that you trained from with the data that comes out of our generative model. Does it match the distribution or not? So on the far left, what you're seeing is the choice of atomic numbers used. And you see in the real distribution, it has this pink color where there's lots of oxygen in the data set. There's no, neon or argon or krypton, these noble gases. And so that's why it has sort of oscillating nature to it. And yet, if you look at the generated elements, it's mode collapse. It's using transition metals. It's using actinides. So that's not great. Meanwhile, the Wasserstein GAN is using most of the periodic table, but it's not learning that some things like oxygen are really common and others are uncommon. And if you look at the diffusion model, now it's matching it really well. It's learning that oxygen is common. It's turning down some of the others. It's not perfect, but it's matching the distribution better. We see the same thing when we look at space group, right? When we look at the space group, we see mode collapse with vanilla GAN. It's using everything, all of its space groups that it generates are between 130 and 160, basically. The Wasserstein GAN uses most of the 230 that are available, but the diffusion model uses most of them, and it uses them at the right ratio that more or less matches the distribution from which it trained. And finally, you could compare the output of these things in terms of their predicted properties. So when you look at the actual predicted properties for real materials in terms of band gap or formation energy or modulus or whatever, and then you look at the output of these models and you predict those, you're gonna, when you compare these violin plots, it sort of looks pretty convincing there as well. Okay, so all that said, I think that we are now approaching what I'm going to call utility. Just like this picture of a face from 2017, it's not perfect, but it's good enough that I could start doing something with it if I was, using generative faces for movies or whatever else. I think that we're in kind of the same position with generative models for crystal structures. They're good enough to be useful. Some of these things actually look like they are on the convex hull, meaning they're stable. They look like we could probably make them. They might be interesting in terms of properties, so they're probably good enough to start doing something with them, even if they're not perfect. So this paper just came out this year. We had the preprint out for a while, but the final published version is now out in Digital Discovery, and you can sort of follow along with it. But we think it's a pretty big step forward. And clearly, as models get better, diffusion is sort of the star right now, but in 6 months when something else is out there, I think you're going to see these generative models that are just going to continue to get better and better. Okay, so then maybe a next good question would be, okay, so you can generate something. Can you generate something new that's also interesting, meaning unexpected? So this work was led by Sterling, my student, and his summer student, Trun. And what they were basically creating is something we call the Discover algorithm. Discover stands for descending from stochastic clustering variance regression. And essentially what it lets us do is search for materials by penalizing you if you return something that is similar to something it's seen before, right? So how did we do this, and why did we do this? I was interested in chemically interesting materials, but the problem is that it's hard to even define what I mean by chemically interesting. Like if I ask the people on this Zoom call or Teams call today, to complete this matrix, where I want you to fill out this matrix and put a number between 0 and 1 if something is more similar or more dissimilar to its other elements, the other formula, I don't think people would know what to do here, right? Everyone would come up with their own metric because there wasn't a single good metric that I could think of that allowed us to measure chemical similarity. And yet a group out of University of Liverpool came out with just that. In the year 2022, they came out with this paper that basically, or I guess this came out in 2020, they came out with the element movers distance, which uses the Wasserstein distance, but applied to the composition-based feature vector. And it allows you to now effectively compare different formulas in a pretty effective way. So once they had made that, I actually went to the University of Liverpool for my sabbatical in 2022, and we used that metric to generate this Discover algorithm. Once we had a measure of how chemically similar or dissimilar things are from the formula, we can do something called dense map embeddings. And embedding is simply when you take a high dimensional representation of a material, like this big vector that I showed you earlier that represents a material, for example, and you can now compress that down into 2 dimensions. That's called an embedding. But we're not only going to do an embedding, we're going to do a density aware embedding. So now what you see in this color map, in the regions where it's bright yellow are the spots where we have lots of materials with chemically similar formulas. And the regions in the dark blue are regions where there's no materials out there, right? So they're very dissimilar. In other words, maybe those are interesting materials, or maybe there's no material that can be made over there, right? Why do we like this? We think this is really great because now for the first time, we have a quantitative way of introducing a new axis for chemical uniqueness in our discovery pipeline, right? So for example, maybe you're using machine learning predictions on the y-axis. This is predicting whatever, strength or whatever else. But now on the x-axis, we can now have this quantitative way of expressing chemical uniqueness. So if you work at a company and all you care about is some new compound, it doesn't have to be very chemically interesting. So you don't care if it's in a region where there's lots of other ones, as long as it does better, great. But maybe you're an academic and what you really want is discovery, and you want to move into these regions of unknown and unexplored space. Well, now you have the tool to explore that one as well, or anywhere in between. So we tested it out. we took this data set of bulk moduli values from DFT calculated bulk moduli. And basically, if you look at the real distribution, it looks like this, where, I don't know, the vast majority of materials don't have a bulk modulus over, say, 300 gigapascals. So we took all those, the top 2% high performers, and we put them in a hidden validation set. We allowed the model to train off of chunks of the other data set at a time, 100 data points at a time. We allowed it to train, and I think we gave it 900 cycles of training on 100 at a time. And we were basically asking, can it find these extraordinary materials? Can it extrapolate? And can it do so while finding interesting new materials? So here's the metrics we're going to compare. First off, of the top 2% that we hid, how many does it find? The second one is, okay, how many additional unique atoms did it find that it didn't have in its first original 100 data points? And then similarly, how many additional new unique chemical formula templates did it find? So instead of like, Al2O3, that's a 2-to-3 ratio, did it find new interesting ratios of formulas to use? And the way that we're going to compare it is by doing random search as our baseline. But then we're going to do the discover algorithm tuned 3 different ways. One where it's weighted on performance, one where it's weighted on a mixture, 50-50, and one where it only cares about novelty. And here's what we find. So in this plot, take a look at this top row. This is showing you how many of those top 2% materials did it find. The 4 columns represent the 4 models. So this top left represents random search. And unsurprising, even after you do 900 rounds of randomly picking 100 compounds each time, it only finds about 20 of the top 2%. So not very good. But if you look at the performance algorithm, it's able to find those top 900 really quickly, quite effectively. And then if you do the novelty algorithm where it's just trying to find interesting chemistries, it doesn't find them, right? Because that wasn't the job in that case. And if you do this 50-50 mixture, it kind of does okay at both. Same thing with new atoms. If you search at random, then you will find the atoms quickly. But if you search based off of performance, it will not find new atoms because, again, it was focused on performance, not necessarily novelty. And then in the middle, you see this really great balance between exploration and exploitation. Same thing with chemical templates. So we think this is a cool approach. We think it's validated that this is a tool that people can use to, while they're trying to find new materials, make sure that they're finding interesting ones, however they define that. Okay, and you can follow along with this. Everything that we publish out of my group is on GitHub. It's openly available. We try and make tidy, well-commented code that you can follow along with and actually reproduce and use yourself for something afterwards. Okay, finally, in the rest of my time, I'd like to talk about how we are now using machine learning to accelerate traditional structure prediction algorithms. And this was work that I did when I was on sabbatical at the University of Liverpool over the last year with Matt Rosinski's group. And the student I was working mostly over there with is this Chris Collins guy. He partnered with my student Hassan, and we had some help from others, John Claridge and others who were very helpful in this process. Let's get into it. So the traditional way that materials get predicted very often is by thinking them as in terms of different subgroups. For example, strontium titanate can be thought of as an intermixture or an inner growth of the titanium, rutile structure, and this strontium oxide roxol structure. Right? If you combine aspects of those two materials, then you end up with this perovskite structure. Okay. So what you could do is that you could predict a crystal structure for any composition that you wanted, right? Take this ternary space. I could, at every single point on this graph, I could predict a structure, and ideally I would do so in a way that I eventually find the 10 or 12 different actual lowest energy structures. So I'm gonna, for every point, do a calculation, come up with a structure, and then compare that structure with everything around it to figure out whether it's the lowest and therefore whether it's thermodynamically stable or not. So that's the problem, is that for every single point on this map, I have to come up with a structure prediction, and it's got to be a good one because I'm going to compare it to others to try and find the lowest. So that's hard because predicting structure it's expensive. Even for simple structures, like relatively simple ones, they can be really complicated. Like here's quartz. Quartz has your 6 lattice parameters, right? ABC, alpha, beta, gamma. And then each atom has the 3 position parameters. So ignoring occupancy, ignoring thermal displacement parameters, just the positions of things gives you a 33-dimensional problem. And this is for a single structure. So how do you find the optimal values of those 33 dimensions? Well, there's different things you can do. You can do local optimization. You can do, basin hopping. For example, here, maybe if you find a really bad structure, you start following the gradients down, and then you do some hopping to randomize this until you find hopefully the best one. But this is slow. If you're doing that over lots of materials, it's going to be a really slow process. So our friends in Liverpool came up with a better way. They did it by thinking about how different modules might exist and how you might stack those modules together to create a structure. So think of like Legos. If you play with Legos, those little building blocks, imagine taking little different Lego pieces and assembling a structure by pre-assembled building blocks. That's kind of what they're doing. Like here you see that one module might be these corner shared octahedra, right? Or maybe it's an alternating group of corner shared octahedra. So in this case, we go from a module to a submodule. Okay, so they published this paper in Faraday Discussions in 2018. They called it the Flexible Unit Structure Engine for basically predicting structures. So essentially, they have to pick different available crystal systems. They have to say, okay, if these are going to be, if we're going to create modules out of these, like our cubic module, right? You can imagine that you could stack these things together such that the overall geometry is cubic or tetragonal or orthorhombic or all the different unit cells, right? Then you have to come up with your submodules and figure out how they get decorated, right? Is it just a plain one on the corner that gets repeated? Or is there like a centering operation or something else, right? Here's all your different submodule motifs for where your anion and your cation can exist in your material. Once you have your different, modules, then you decorate these submodules into the overall structure by stacking them together, right? So we go from the group of our submodules, we make layers, we stack the layers, we end up with a structure. So this works pretty well, but the catch is that you have to do this for many, 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 many materials. Like here, they're showing you 10,000 DFT calculations. Now, these aren't the slow full DFT calculations. These are using force fields, which are just sort of okay. But after they do 10,000 versions of a structure for a single chemistry, they pick the most stable one, right? They say, okay, here's the lowest energy one that we found. It's probably the real structure. And when they actually tested this, they tested it in this yttrium, strontium, titanium oxide system, and they were able to find them, right? They were able to look and map out this whole system and find the actual materials. Of the 10 structures that exist in that phase space, they were able to find 9 of them using this approach. So looks pretty good. Looks very promising, but it is slow, right? Because they're doing 10,000 DFT relaxations, and that's just way too slow. It's not an option. So how do we speed that up? Well, you could imagine that some of these really high values of X, those correspond to structures that were totally bonkers, like totally not worth testing at all because they were so far from what was realistic. But how do you know that ahead of time? Well, one way is you could find patterns in the data via machine learning to toss out these materials that you know are a waste of time and focus on the ones that are actually likely to exist. So one way to do that would be to predict the lattice parameters more accurately. Going back again to this idea of the lattice parameters, they had to assume a lattice parameters for all these structures. And the way that they made their assumption was based off of simple cation coordination environments and this idea of atomic or ionic radii. For example, if you're trying to figure out this length of the blue square here, A, then you would say, well, it's equal to 4 red radii and 4 brown radii, just like you probably did in your intro to material science course. Well, the problem is that the values that you might use for the different radii totally depend on the coordination number, right? So here you see chromium, right? Chromium 4+, if it's 4 coordinate or 6 coordinate, look at that. That's like 30% difference, right? So which value do you use if you don't know the coordination number? Especially because we're trying to figure out the coordination number, which we get from the structure. So it's like a chicken and egg thing. So no wonder they had lots of bad starting points for volume. So me and Hassan said, well, we can fix that. We can just predict the average volume per atom, and you'll be able to calculate the lattice parameter much more accurately. So unsurprisingly, many of the different classical models are able to predict the volume per atom in a structure really with high fidelity. That's not too surprising, but it is useful. So once we were able to predict these things with pretty good accuracy, we can now feed it to our model, and we can compare the original Fuse model with Fuse plus this machine learning approach. And what you're seeing in these different rows of the comparison is how well we do in this process. Is it faster? Is it more stable? How often does it get it right? Does the job crash? And basically what we see is that it's just better. It's significantly better. It's faster. It's more stable. It doesn't crash as often. And this was for a compound that it had never seen before. This was brand new out of their group. Here's another one that came out of their group. Totally brand new. Did significantly better at predicting the structure. Here's another one. So we think that first off, this approach seems to work, but we can probably do even better. Because remember, all we've done so far is predict the lattice parameter so that the DFT step was faster. What if we did something different? What if, for example, we used one of these models that takes a given chemistry and predicts a structure? Just like the stuff I showed you earlier today, when I showed you those generative models that can generate structures. What if we used those and we predicted a bunch of the most likely structures? We broke them up into little building blocks, and then we used those building blocks in the fuse model to reassemble them, right? So for example, let's say that we predicted this as one of the candidate structures. In their fuse approach, they can break this up into these submodules and then only use these submodules when trying to assemble the best structure. So I don't know, my kids love to play with Legos, and they take the entire box and they pour them out on the floor, and there's Legos all over the place. And there's so many, it's sometimes hard to know what to do because it's overwhelming. What we are essentially doing is saying, okay, don't take the entire box of modules, take these select few that are likely to be the best ones. And what we see here in that process is that it dramatically speeds up the process. So here's those same three materials. Here's how long it took with the regular fuse process: 5 hours to resolve the structure, 2.5, 2.8. And now when we use this machine learning, generative approach where we're limiting the design blocks to use, we're able to get better structures, which I'll show you in the next slide, dramatically faster. Multiples faster, 3, 4, 5 times faster. I think in some cases we're seeing up to 8 times improvement, and we're getting more stable structures. The structures that come out at the end are more thermodynamically stable, we think. So we tested this not just on these 3 materials from, that they had discovered that year, but we tested it on 8 or 9 different materials that span the breadth of the types of structures you see in inorganic chemistry. And across the board, it does extremely well. Again, between 2 and 8 times faster in terms of how long it takes to do these. And it's better in almost every case, except for this funky one, this yttrium tungsten boride, where it goes a little bit slower. But generally, it's much, much faster, which is exciting. And also that the structures that are generated are much more stable. We're talking like significant, over 50 MeVs more stable in many cases, which is pretty awesome. Okay, you can follow along with that one. The Chem Archive article for that one is out. Hopefully the published one will be available soon. But I hope that this has been insightful to show you some of the things that machine learning can do for computational material science. And if you're interested in computational material science, here is a journal which I hope that you'll consider submitting articles to. I'm an editor at Computational Material Science. It's a good journal. If you send anything related to machine learning, it will go to either myself or Tom down below. We handle all the machine learning submissions, and I'd like to imagine that we do a pretty good job to get your response. And if anything I covered today was interesting to you, then I think that, if you didn't know where to get started yourself, if you wanted to do materials informatics, we have some great resources. On the right is a YouTube playlist I have put together, and it's getting longer all the time as I add more stuff to it, where I go through all the stuff that goes into materials informatics, like how do you build models, where do you find your data, how do you featureize your data, what different algorithms are available, and which one do you pick, right? We get into all that in this playlist. And we also run a podcast called Materialism, which we are really excited about. We've been doing it for about 5 years. We cover all sorts of interesting and fun and emerging topics in material science, as well as the cool old stuff that has been happening in the past. So with that, I'm happy to take any questions.
If I can start, Professor Spark. So I have the question of all this work is academic only, or have an application in industry right now, or
it's a great question. Yeah, great question. We have a fair bit of our work sponsored by industry. For example, we have one PhD student sponsored by Northrop Grumman, where he's making rocket propellant. So if you're going to send satellites into space, right, how do you get them there? He's using these informatics approaches that I've described for generating new fuel mixtures. I have another student sponsored by industry from a dental company making dental resin composites. So when you get a tooth filled, sometimes they use amalgam, like the metals, but it's better to use these resin composites. And he's actually generating new resin composites for that dental company. And then we have a couple grants with industry where we're going to be applying these same types of tools to polymer processing to make better polymers by using informatics. Not in all of those cases are we doing generative models where we're actually generating new structures, but we are using generative models to come up with new formulations, to come up with new processing parameters. So yeah, this is very, very relevant to industry. The work I've showed you today is largely academic, but a lot of what my group does is pointing at industry.
Thank you.
Other questions? Yeah.
Are you going to recreate these materials in real time, or the formula that you're creating in the computer?
We're doing both. My group is interesting. At the University of Utah, we have a lab where we are experimentalists. Like, that was my background. Before I became a professor, I was completely an experimentalist. I just made things and tested them. And we only in the last 10 years have started doing machine learning. But my lab both synthesizes and predicts a lot of materials. And we also partner with people. We have a lot of collaborators where we send them the outputs of our models and we say, what do you think? Any of these worth making? And they can look through them and we can decide which ones are worth spending our time to actually synthesize. So yeah, we are definitely doing both. Other questions? Well, I'll just say that if anybody's interested in this topic, by the way, you can see these resources here, but we are also always looking for good graduate students. I hire every year 2 to 3, students typically on any given year. We have a pretty big group here, and my department at the University of Utah is also fantastic. We have like 25 faculty. It's one of the big material science departments in the United States, and there are people doing, about half the department does traditional metallurgy. So we have one of the world's experts in titanium, for example. He invented the hammer process, which is now innovating titanium production. We've got people doing alloy development, aerospace. On the material science side, we have everything from batteries to biomedical to you name it. And we are always looking for good grad students. So hopefully I'll see some of you here in Salt Lake City.
So how can I apply for the university or anything that you are mentioning?
The easiest, if you go to mse.utah.edu, you'll find a link to graduate school resources, including the application. We have started waiving the GRE, so you don't have to take the GRE, which is really nice. I think it's worth applying. In fact, if you're a strong applicant, some of our best students we actually waive the fee for, so then it doesn't even cost you anything. In other words, if you think you're a good student, we'd like to talk to you. Okay, anybody else?